welcome you all to a new topic that is called electrostatics, and which is a part of a very wide topic called electrodynamics. We are discussing a very small part of this very large topic that is called electrodynamics. Okay, before that, let me introduce you to a new force. Probably you might be aware of that in your +2 classes, but anyway, let me introduce you to a new force, okay, which is a billion and billion times stronger than gravitational force, and which varies as same as that of the square of the distance between the two matters. But unlike gravity, in gravity you know that there is only one kind of force, that is attractive force, and one kind of matter, that is our mass. But in this new force you have two kind of matters. One we call it as positive and other we call it as negative. When the same type of, that means positive types comes together, they will repel with this much amount of enormous force, that this billion times force. And when they are unlike kind, that means when one positive and one negative comes together, they will attract with the same enormous force. So if you mix them evenly together, that means if you mix the positive and negative evenly together, you can make everything that you see around you, everything, you, me, and everything that you see here is made up of this positive and negative charges. And when you look into the atom, you know that these positives are called protons and these negatives are called electrons. Everything that you see is made up of protons and electrons, and obviously you know that there is chargeless particles that are called neutrons. Okay. Anyway, in this electrodynamics, we are studying about these charges. Okay. Now, what is the idea, or what is the aim of electrodynamics? Let's check that. Okay. So imagine that you have two charges. That one charge is, you name it as Q. So here you have a charge Q, and I call it as a source charge. Why I named that, I will tell you later. This is called a source charge, and here you have another charge that is called a capital Q, and we call it as test charge. And in physics, you know that to discuss anything we need a coordinate system. For that, let me draw a coordinate system here. That is, you have a coordinate system with some x, y, and z axis, and let this be the origin. Now, to specify the position of anything in space, we use position vectors. So to address this small q and to address this capital Q, that is the test charge, we need two position vectors. So let me draw those position vectors. So this is the position vector of the first charge, that is the source charge, and here is another vector, that is the position vector of the test charge. And let me denote it by r dash. This is the vector r dash. So you have to be careful about the notation because we are using it entirely in this course. This is r dash and this is called r. So you have two vectors. Now imagine, now we want to find the force due to this small q on this q. That means we want to find the force due to the source charge on the test charge. How could we find that? Probably you came with an equation that you have learned in the +2 classes, but wait a little, I am making it more complex. That is, this r dash and r are not just a stationary vector, they are moving. How? They depends on time. That means r dash is equal to some r dash of t. That means it moves, or the vector varies with respect to time. and r also, this r also, that is the position vector of the test charge, is also vary with respect to time. So you have two vectors, two position vector, they are moving. What does it mean they are varying with the time? Simply they are moving, that is this charge, source charge and test charge is not stationary at all. That is the problem here. So what you have learned in the plus 2 classes, that is simply the Coulomb's law is not applicable here because they are moving. When they are moving, the force on this test charge, the force on this test charge will depend on many factors. Basically the product of the charges, the distance between them, not only that, the velocity with which they are moving, velocity, acceleration and many things, and the expression for the force will be very complex. So the whole aim of electrodynamics is to find this equation. Which equation? The equation of force on a test charge when the charges are moving. But in plus 2 classes you have learned something else. I am coming to that. That is the topic for this electrostatics. Now this equation is very complex because the charges are moving. So you know that when you learn physics or any kind of subject, we will go from some simple steps to the higher and higher level. So we are taking, or we are stopping its movement. We are taking r of t or r, these two vectors, to be a constant. So this does not move, that means this is a constant and this is also a constant, which means that the charges are not moving at all. They are stationary, or in other words we can call it as static. Okay. So in electrodynamics we deal with, or finally we deal with the force due to moving charges, but here we are dealing only with the stationary charges. That particular part of, or particular branch of this electrodynamics is called electrostatics. Okay, that is when the charges are stationary, how do they interact, what is the force between them, what is the electric field and everything. Okay, basically the force, how we could find that. That is the topic of today's class, that is electrostatics. So today, so we are dealing only with electrostatics. Actually it is a single word, but I put the space purposefully because statics, that means the electro means the charges are stationary, or electrostatics means stationary charges. We want to find the force between them. So now today we are dealing with electrostatics. Now let's find the force between two stationary charges. That you have a charge as discussed before, that is one Q, and we call it as the source charge. This is the source and this is the test charge, that is capital Q, that is the test charge. So we call this Q, this small q, as source because it is the source of force on Q, that is this charge small q is exerting a force on the capital Q. That is why this charge is called a source, and to test that force, that means to measure that force, we use this capital Q, that is test. That is why the name source and test. Okay, before going into that equation, again we set up a coordinate system. So we have the origin here and the position vectors too. So the first position vector, second position vector. So the first position vector, that is the source vector, is called r dash, and the second position vector is called r. So we have r and r dash, and now onwards from electrostatic point of view, this r dash and r are fixed in space. That means the charges are stationary. Now let me draw another vector which has to be drawn always from the source to the test charge. So I am drawing another vector, that is from source. This has to be drawn always from the source to the test. That is a convention that we follow. Then only we can do all the problems dealing with this electrostatics. If you follow this this kind of notation, that is r dash for the source and r for the test and the separation vector, and we call this as the separation vector. Why? That is the separation. That vector actually separates the source and the test. Okay, so we call it as the separation vector. And denoted by the curly r. So now you have three r's, that is r dash, r, and this curly r. This is always used for separation vector, and these r's are for position vectors. Now you can see here, this is a triangle. That means with the sides r dash, r, and the separation vector r. Let me write it once more here. So you have three r's, and with that r sides we have a triangle. Now the triangle has sides as vectors, so we can apply triangular law of vector addition here. So in vectors we use triangular law to sum vectors. Here you can see this is r dash, the head of this is connected with the head of the r dash is connected with the tail of the separation vector. So they are summing up. That means this and this is summing up. So we can write it as r dash plus r, that is the curly r, this is equal to r. This is the sum. Or from this we can write r is equal to r minus r dash. So this is a very important relation, because we use this convention everywhere when we are dealing charges, and when we need a coordinate system and to find the separation, we use this relation, that is r is equal to r minus r dash. That means the first one is the position vector of the test charge, and the second one is the position vector of the source. So you got it. Now let's write the expression for the force due to this small q on capital Q, and that equation, let me write it directly, and which is not at all derived. It is calculated in historically, it is actually calculated experimentally. So it is an experimental law. F is equal to 1 by 4 pi epsilon 0, then the first charge q into the second charge q divided by r square into r cap. Okay, so this is the expression for the law, and this particular law is called the Coulomb's law. That is, this is called the Coulomb's law. Okay, let's discuss each terms in this equation. The left side we know that this is the force, and the force is a vector quantity, and here epsilon 0 is a new constant which is called the permittivity of free space, and q is the magnitude of one of the charge, that is the source charge, and capital Q is that of the test charge, and r, here you can see two kind of r. One is r without an arrow, and another r that is without a cap, with a cap. So there are two kind of r. What is this first r? This first r is actually the magnitude of the separation vector. That means exactly the distance between them. Actually, what is how much, that is we can measure it in meters in SI unit. That is, what is the distance between them, that is given by r, the square of that distance. Now what is this r cap? R cap is, already we know that in vector notation we use cap for unit vectors. So r cap is the unit vector. Okay, that is the unit vector. Unit vector has, we know that, as you know that unit vector has a magnitude always 1, and it has a particular direction. What is the direction? R cap has the direction as same as that of the separation vector. That is, r cap has same direction as that of separation vector. So That means this is the separation vector. This is the direction of separation vector. That means it is directed from the source to the test. It is always directed from the source to the test, and r cap also has the direction like this. Now let us find where this force comes. Okay, let us draw that force. Okay, now we are actually drawing the force on, okay, we are actually drawing the force on this charge q. So that is given as F is equal to 1 by 4 pi epsilon 0 q into q by r square into r cap, which has the same direction as that of the separation vector. Why we used this r cap here? Because force is a vector. If you write this equation without that r cap, that is not complete. Then only the magnitude is what we are discussing. Since force is a vector quantity, the left side is a vector quantity, then the RHS, the right hand side, should also be a vector quantity. That is why we used the r cap there to specify the direction of the force. Now let us see what is the force. We are measuring the force on this capital Q due to this Q. That means we have the force law, that is F is equal to this much. And now what is the direction of action of this force that we want to find? How will we draw that force vector in this diagram? That is we are going into. Now the force is directed along the direction of r cap, that is given here. That is, the direction is given by this r cap, that is the direction of the separation vector. So the separation vector is this, it is directed along this line, along this direction. And the force is acting on the charge capital Q, that is, it is acting on this charge. So from here it is acting along the direction of the vector r. So the vector r follows this direction along this line. So our force is also following, the force is also following this direction. Yes, this direction. So this will be, this yellow arrow is the direction of the force. It follows the same direction as that of r. So what it is actually doing, this is actually pushing, that is the source charge is trying to push the test charge away from it. That means they are repelling each other. Why it is repelling each other? Because we have taken Q and capital Q as positive. What if it is one of the charge is negative? Do we need another equation for that? No, no need. That itself contained within this equation. Let's check that example. Okay. So, okay. So what we are talking is that is, do we need a separate equation to show that if the one of the charges is negative and the other charge is positive, then do we need an additional equation? Do we need an additional equation to represent the force? That means here we know that now this force show the repulsion. Now for showing the attraction, do we need a second equation? Let's check that. Now imagine that now I am replacing this charge, okay, I am replacing this charge with minus q. Now I am using a new charge minus q. Now this is minus and this is plus, then this should be attractive, we know that. So let's modify the equation based on that. So now our new equation becomes F is equal to, that is actually not the new equation, we are substituting the values of Q and whatever you see here into this Coulomb's law. Okay, so F is equal to 1 by 4 pi epsilon 0. So instead of Q I have to put minus Q, so let it be there, and into Q divided by r square, there is no change in the separation, and into r cap. So as at first sight you may think that F is directed again along the direction of r cap or along the direction of r, that means towards this direction. So you may think like that, but just a moment, let me rearrange this equation, that is 1 by 4 pi epsilon 0 q into q by r square into, let me take this minus and put it along with the r cap. So now what you see? Now you can see the direction has been changed. The magnitude has no change because they are again the same amount of charges, the same separation. So there is no change in the magnitude, but there is a change in the direction. That is, in the previous case, the direction was along r cap. Now the direction is along minus r cap. That we know that a vector is directed along this direction, let A, and what would be the direction of minus A? That will be exactly opposite to that. So similarly, if r cap is directed along this direction, then the minus r cap will be directed opposite to that, something like this. Okay, so this is exactly opposite to that of r cap. That means this is the direction of this new force. New force means when we are using a minus q and a plus q, the force becomes something like this. So now we can see that is now the force on q due to the source charge is along the direction of the minus q itself. Now what does that mean? That means the q, the test charge, is getting attracted towards the minus q. So the information about the attraction, repulsion and everything is buried in this equation. You have to only change the value of q. If it is minus q, you can put minus q. If it is capital Q is minus q, you can put whatever be the value. If both are minus, what will happen? That is minus, this will be minus, this will be minus, so minus times minus, it becomes plus. That means again it is along the direction of r cap. That means it is towards here, again repelling. So all the meaning of it is contained within this equation. Okay. Now let's move. What if there are multiple charges? That means now you have only one charge q here and a test charge. What if there are multiple source charges, some q1, q2, q3, etc.? Let's look into that. So imagine you have a charge q1 here. This is one of the source charges, and one q2 here, and one q3 here. And we want to find the force due to all these source charges on a test charge, that is capital Q here. So for that I am not again setting up all the coordinate systems. We know that it's there. I am only drawing the separation vectors. Let me draw the separation vectors. So this is the first separation vector. So separation vector is always directed from the source to the test. So this is the second one, and this is the third one. Now we have three separation vector. Let me name it as, this is as R1, okay, R1, okay, so this is R2 and R3. Now you have three charges. Three charges means you can see, you can find many pair of forces here. One is q1 and q, q2 and q, q3 and q, then q1 and q, q1 and q3 and q2 and q3. That means you can find many pair of forces here. So if there were no other charges, that if q2 and q3 were absent, you know that the force is only because of q1 and q. You can easily calculate this using the previously learned Coulomb's law. But here the problem is, when you are calculating the force due to this q1 on q, actually the other two charges is also exerting a force on q1, also they are exerting a force on q. Do they complicate these things? No. Here we may feel that there are multiple forces, so it may complicate the thing. Here a new theorem or a new principle comes to rescue us, that is superposition principle. So what it says? So to find the force due to multiple charges, what you have to do, you just take first pair or any one of the pair. So I am taking the first pair. The first pair is q1 and q. Let me write the force between them as F1. And superposition principle says that when you are considering one pair, you just ignore the other. You just ignore that q2 and q3 are there. Okay, and I am ignoring that. Now I have only q1 and q here, and I know how to write it from the Coulomb's law, that is 1 by 4 pi epsilon 0 q1 into q by r square, sorry, here it is r1, so r1 square into the direction of r1 cap. Okay, now it's fine. The second thing what you have to do, and what would be the direction of that? Let me draw the direction too. That is q1 is exerting a force on q along the direction of r1 cap, so the direction will be this. Let me take another color. So this will be the direction of F1. So this is the direction of F1. Now take the second charge, that is Q2, and now consider only Q2 and the test charge, Q2 and Q, and ignore others. Then write the expression for the force, that will be F2, that is equal to 1 by 4 pi epsilon 0 Q2 into Q by R2 square into R, you have a cap, R2 cap. Okay. So the direction of that will be along R2, so that means it's along this direction, and this is F2. And the next one is Q3, that is Q3 is exerting a force on Q which is F3, so F3 which is equal to 1 by 4 pi epsilon 0 Q3 into Q divided by R3 square into R3 cap, and which is directed along this direction. So what we have done is that you just take all the pairs, that is the pairs that is exerting force on our test charge, and find the each force individually, ignoring the others. So that is F3. Now how to find the total force? That total force is F3, sorry, F total, let me write it as F total, which is the sum of this F1, F2, F3. That means F total is F1 plus F2 plus F3, but you cannot add it just like three numbers. You cannot add it algebraically because they are all vectors. So you have to take the vector sum of F1, F2 and F3. Okay, this is what superposition principle says. That is, if you have multiple charges, to find the force due to all of them, you take each pair individually and find the individual forces and take the vector sum of that. That is very important. You do not just add, you have to find the vector sum of those forces, then you get the final force. And if you have n charges, you can add F1 plus F2 plus F3 plus etc. That is how we find the force due to multiple charges. So if you have 3 charges, you can find it like this. And what if there are n charges? Now the expression becomes something like this. You have n charges, then the total is F is equal to F1 plus F2 plus etc. up to Fn, and note that they are all vectors, and find it sum, or simply we can write summation over I is equal to 1 to n Fi. You take the sum due to all the charges. This is how you can find the force due to multiple charges. And we are concluding here. The next class we will discuss about electric fields and Gauss's law, etc. And thank you.